All right, welcome everyone to this detailed explainer. Today, we're going to completely demystify the Java collection framework. As an instructor, my absolute main goal here is to guide you step by step through what is easily one of the most powerful and essential architectures in the entire Java programming language. We're going to break down the core concepts, examine the code, and map out exactly how you can manage data dynamically. So get focused, maybe grab some notes, and let's unlock the true potential of Java collections together.
Here is our roadmap for today. First, we'll cover the array limitation. Second, the collection framework hierarchy. Third, lists, which are ordered and indexed. Fourth, sets, unique elements only. Fifth, queues, which follow first in, first out. And finally, number 6, maps, key value pairs. Okay, let's jump right into section 1, the array limitations and the collection solution. To truly understand why the collection framework even exists in the first place, we have to start with a classic developer problem. Imagine you're building a piece of software, and you need to store some user data. Well, the most basic tool you have is an array. But traditional arrays come with a strictly rigid constraint. They have a fixed size. If you create an array to hold exactly 10 integers, and suddenly an 11th user registers, well, that data is lost. You just can't increase the size of that array at runtime. On the flip side, if you allocate space for, say, 50 users and only 2 actually show up, you're just wasting valuable memory. So collections are the ultimate solution to this. They are dynamic data structures that automatically grow and shrink exactly as your application demands. Plus, they come loaded with heavily optimized, ready-made methods for searching, sorting, and manipulating all that data. But wait, there is a vital academic rule you absolutely must remember here. Collections can only store objects. They literally cannot store primitive data types like a lowercase int or a float. So you might be wondering, how do we store simple numbers then? Well, Java provides something called wrapper classes. These are basically object-oriented alternatives to primitives. So instead of using a primitive int, you'd use the capital I integer class. This acts like a bridge or a VIP pass, wrapping your primitive data securely inside a valid object so the collection framework can actually accept it. Moving right along to section 2, the collection framework hierarchy. Okay, let's dive into this blueprint. At the very top of our structural tree, we have the iterable interface, which is the absolute root. That branches down into the collection subinterface. And from collection, the family tree splits into 3 main branches: list, queue, and set. Now, notice off to the right there, map sits in its own entirely distinct hierarchy. It actually does not extend collection at all. The concrete classes you'll see branching off, things like array list and hash set, those are the actual implementations of these theoretical interfaces that we'll be writing our code with. All right, let's tackle section 3, lists. They are ordered and indexed. So let's open up our developer toolkit and examine our very first interface, the list. If you're in a situation where you need order and absolute predictability, this is exactly where you start. The defining characteristic of a list is that it maintains the exact insertion order of your elements. Every single piece of data is assigned a strict, zero-based integer index, 0, 1, 2, and so on. And because of this strict indexing, the list interface is actually incredibly forgiving. It freely allows you to add duplicate elements, and you can add literally as many null values, meaning completely empty, uninitialized data points as you want. This perfectly illustrates the most popular implementation of the list interface, which is the array list. Looking at the code snippet, we create a dynamic array. We can add A, B, and C. Now, because these elements are stored in contiguous memory locations, fetching data using its index, like, say, grabbing the item at index 2, happens incredibly fast. We call this O of 1, constant time, meaning it takes the exact same instantaneous amount of time regardless of how massive the list gets. However, you really need to be aware of the drawback here. If you insert or delete an element right in the middle of an array list, it causes a significant performance drag. The system literally has to physically shift all the subsequent elements backward or forward in memory to adjust for that new space. But array list isn't your only option here. We also have linked list and vector. Linked list uses what's called a doubly linked list under the hood, so the memory isn't contiguous, which means insertions and deletions are blazingly fast because you're just changing pointers, no shifting required. But the trade-off is, it takes up more memory to store those pointers. Vector, on the other hand, is a legacy class. It behaves almost identically to an array list, but it's strictly synchronized, which means it's thread safe. If multiple threads try to access a vector, only one gets in at a time.
This strict lock makes vectors significantly slower, which is honestly why we rarely use it in standard single-threaded modern applications. Let's shift gears to Section 4, Sets, Unique Elements Only. Moving onward, we are leaving behind the ordered, neatly indexed world of lists and entering the domain of the set interface, where absolute uniqueness is the absolute rule of law. Let's draw a direct binary contrast here. Where a list welcomes duplicate entries and organizes them neatly by index, a set acts kind of like a strict bouncer at an exclusive club. If your name is already on the list inside, you're not getting in. A set will instantly and automatically reject any duplicate entries. Furthermore, standard sets are completely unordered and unindexed. You can't say, hey, give me the element at index 2, because index 2 simply does not exist in a set. Now, what's really interesting here, if you look closely at this code, is that the name Vibolf is clearly added twice. But in the final console output, it only appears once. The hash set quietly, completely discarded the duplicate. Also, notice that the output order is totally randomized. It doesn't match the order we typed it in at all. That's because HashSet is backed by a hash table, so it places elements purely based on their internal hash codes, which is exactly what gives us that incredibly fast O1 performance I mentioned earlier. But what if you need uniqueness, and you also need your data to be perfectly sorted? Well, enter the tree set. Backed by a red-black tree architecture, which is a self-balancing structure that constantly reorganizes itself, a tree set actively sorts your data every single time you insert an element. So your integers will automatically print out in perfect ascending mathematical order. But there's always a trade-off, right? It's slower. It takes O log n time. And crucially, you have to remember that because it constantly compares values to sort them, a tree set absolutely forbids null values. If you try to insert a null, it will trigger a null point exception right away. Next up, Section 5, Queues. First in, first out processing. Let's shift our focus to the queue interface. Honestly, if you've ever waited in line to buy a movie ticket, you already understand exactly how a queue operates in Java. Queues follow a highly predictable, strict FIFO principle, first in, first out. Think of that physical ticket line. Elements are always inserted at the rear, the back of the line, and they are exclusively removed from the front, the head of the line. The very first person who got in line is strictly the first person who gets served and removed. Now, because queues are all about managing data flow, they actually provide two distinct sets of methods for their primary operations. If you use add, remove, or element, and something goes wrong, like maybe the queue is empty when you try to remove an item, Java will aggressively crash your program with an exception. However, if you use the alternative methods, offer, pull, or peek, Java acts much more safely. If the queue is empty and you call pull, it won't crash. It will simply and safely return a null value. But hey, rules are meant to be broken, right? A priority queue completely breaks that standard FIFO rule. It doesn't care who got in line first. Instead, it allows VIP elements to literally skip to the front of the line based on something called natural ordering. Notice in our example code that the strings are entered randomly, but they are processed alphabetically based on their ASCII values. The string ACTU comes out first, simply because A has a higher priority than B or H. You can even pass it a custom comparator to define your own unique VIP logic. And finally, Section 6, Maps, Key Value Pairs. We have officially arrived at our final, completely distinct branch of our framework toolkit. We're leaving the standard collection interface behind and stepping into the world of maps. Ask yourself this: how would you store a student's roll number so it's perfectly linked to their name, or an employee ID directly tied to their salary? We don't just want single, isolated elements anymore. We want associated data, exactly like a real-world dictionary. This perfectly tees up the map interface. So the absolute golden rule here is this: the map interface represents a data structure storing key-value pairs. It is so different from the rest that it forms a completely separate hierarchy. And the absolute most important academic rule of a map is how it treats its keys. While you can totally have duplicate values, meaning two different students can obviously have the same name, every single key must be 100% unique. If you try to insert a duplicate key, you will silently and irreversibly overwrite the existing data attached to it. Your two main tools in this space are HashMap and TreeMap. HashMap gives you blistering, unsynchronized O of 1 speed using a hash table, but your data will be completely unordered. It's incredibly fast, and it even allows exactly one null key. Conversely, TreeMap gives you heavy but incredibly useful automatic sorting. Backed by a red-black tree, a tree map totally ignores insertion order and strictly sorts your map entries in ascending order based on the keys. Because of this complex sorting, it is quite a bit slower, and it absolutely will throw an exception if you attempt to use a null key.
Before we wrap up, I want to leave you with a really crucial, highly practical academic rule regarding sorting. Standard data structures like array lists don't just sort automatically. To sort them, you have to use the utility class collections.sort, and please note the S at the end of collections there. But remember, collections.sort is strictly for collection objects. If you are ever trying to sort a standard fixed-size Java array, you must pivot and use the arrays.sort utility instead. Don't mix those up. Well, we have thoroughly explored the lengths and depths of the Java collection framework today. You now have the mental scaffolding in place. Lists for ordered sequences, sets for strict uniqueness, queues for line processing, and maps for key value associations. The theory is locked in. The real question now is, when faced with your next complex coding problem, which specific interface are you going to strategically select to build your dynamic application? Thank you so much for learning with me today. Keep coding, keep exploring, and I'll catch you in the next explainer.